Whenever coming up with a value for a parameter, it's important to have some idea of how certain or how sure you can be about that parameter or that value that you computed. And it's also good to have a systematic way of estimating that uncertainty or sureness, a way that doesn't depend on the mood you're in one day to the next. And so in this video, we look at a systematic method for coming up with uncertainty in computed values. We'll start off with a couple of examples and maybe common sense methods for coming up with this uncertainty, and then end up with an agreed upon realistic system for computing uncertainty. Here's an example where we want to compute the power dissipated in an electronic element. And power is the product of voltage, E, and current, I. If we take measurements of voltage and current, each measurement is going to have some uncertainty in it. Now, for this example, we measure 100 volts and our uncertainty is 2 volts, and we measure 10 amps with an uncertainty of 0.2 amps. So it's clear that our power that we compute is going to be 1,000 watts, but what's the uncertainty? Well, we could say that the uncertainty is the maximum range that the power could vary in. So if we measure 100 volts and 10 amps, it could truly be, according to these uncertainty estimates for each measurement, the true values could be 102 volts and 10.2 amps, which would give us 1040.4 watts. Or it could also be 98 volts and 9.8 amps, which would give us 960.4 watts. So if we took this approach, then we would say that our power is somewhere in the range of 960 watts to 1040 watts. More generally, we're going to call this calculated parameter R, and it's a function of all our measurements, x1, x2, all the way through xn. So in this example, R is our power, N is 2, we have two measurements, so x1 is the voltage, x2 is I, and this function of x1 and x2 is just the product, voltage times current. To look at the uncertainty of our computed value, we want to see the effect of changes or uncertainties in each of the measured values. So looking at this function f of x, of single value x, so y is equal to f of x in this example, and if we vary x by an amount dx, then y is going to change by an amount we'll call dy. And this is given by the Taylor series expansion, so f at x plus dx is equal to f at x plus 1 over 1 factorial times the change dx multiplied by the derivative of f of x. And then we have terms for second derivative, third derivative, etc. The first order approximation truncates this to just f at x plus the change in x times the first derivative. So we will say that our new y value is approximately equal to the value of the function at x plus dx times the first derivative. And y is, we said, f of x, so we can rearrange this to get dy is approximately equal to dx times the first derivative of f with respect to x. So back to our computed value where we had this function of n measurements. The change in R is going to be the sum of the change in all the variables, the independent variables, multiplied by the partial derivative of R with respect to each variable. So we have, if x1 changes a little bit, we multiply that by the partial derivative of R with respect to x1, and that's the contribution of the change in R that comes from changes in x1. And we can do that for all of the n variables. Rewriting this in a summation form looks like this. So we have n variables. And now we introduce the notation W for our uncertainty. This W sub xi is the uncertainty in the value of xi. Before xi was voltage and current, so Wxi for the W voltage would have been 2 volts and W current would have been 0.2 amps. Anyway, the uncertainty here is W sub xi, and we're going to say it's equal to this constant. And one quick note is that whenever doing this, one needs to say that assign odds to this uncertainty. So for example, our voltage, the uncertainty in our voltage measurement could have been plus or minus 2 volts with 20 to 1 odds. So there's a 20 to 1 chance that our uncertainty is this value. And if all of these uncertainties have the same odds, then we can write the uncertainty in our calculated value, W sub r, is equal to the sum of the uncertainties times the partial derivatives. And this uncertainty times the partial derivative is the uncertainty due to factor I, or measurement I. Revisiting our example, let's look at the propagation of uncertainty for the power. Again, we had these measurements and these uncertainties in the measurements. So we want to find out what the uncertainty is in our computed value power. Here's the expression that we came up with in the previous slide. The uncertainty in the computed value is the sum of these uncertainties times the partial derivative. And again, here putting these variables into into the right form for this example, shown here. This equation for this example, our change in power is the change in voltage times the partial of power with respect to voltage plus the change in current times the partial of power with respect to current. And just rewriting these partial derivatives, we have I and E. So we can compute that the change in power would be 2 volts times 10 amps, so that's the partial, or the change in voltage times the partial of power with respect to voltage, plus 0.2 amps times 100 volts. And so we get 40 watts for our uncertainty. Whenever we're estimating this uncertainty due to multiple sources, so compound uncertainty, there are different ways to consider the effect of all the different uncertainties. In one case, the uncertainties might cancel each other out. So for example, we have 2 volts uncertainty in our voltage reading and 0.2 amps in our current reading. Well, if we measured 110 for those values, but the true values would have been 102 volts and 9.8 amps, then those uncertainties or errors would have canceled each other out, and so we'd end up with a better estimate. The maximum uncertainty we could have would be the other scenario, where they add to each other. And that's what we did before. So we said that our total uncertainty, the uncertainty of our computed value, was the sum of the contributions from each of the measurements. But this is sort of unrealistic because it's not very likely that each of the measurements is going to be off by its maximum value at the same time. So if we measure 100 volts and 10 amps, it's not likely that the voltage will be 102 volts at the same time as the current is at 10.2 amps. A better estimate would be to take the root mean square of the contributions. What that's saying is that our uncertainty in our computed value is the square root of the sum of the squares of the uncertainty contributions from each of the measurements. There are just 2 more topics to look at, and the first one is coming up with a form for the equations whenever we have a computed value that's of a certain type. The first type is product functions. So in this type, our computed value is the product of our different measurements, and each measurement could be raised to a certain power. So we have a constant c, and then we have a measurement x1, and it's raised to a power a1, measurement x2 raised to the power a2, etc. And this is the type of function that we had for power. We had two measurements, and power was a product of those two. Rewriting that in the form here, this generic form, we had c is equal to 1, a1 is 1, a2 is 1. Another would be this equation for velocity of a dropped object from a height h. So it's a product function. Here c is square root of 2, a1 is 1/2, a2 is 1/2. And now we can rewrite this as a product sum, and we could take out the jth measurement, x sub j, and rewrite it like that, which makes it easy to take the partial of r with respect to j. So here's that, and xj to the aj minus 1 is the same as xj to the aj times xj to the negative 1. And so now we can put this back into here, and we end up with this for our partial. It's just aj, which was the power for xj, divided by xj times the value of our computed component. So here is the uncertainty for r rewritten for a product function. We have, well, here it is in the generic sense, and here we've rewritten this for, this is specific to a product function. So the partial of r with respect to xj is this value here. So then we can take out the constant value r, and we get this for uncertainty of r. Another form is additive function, where we're computing a value that's the sum of all the measurements, and each one has its own coefficient ai. Here's an example, and we can rewrite this example to be in this form. And for an additive function, the partial derivative of r with respect to xi is just the coefficient ai. So we end up with this simple expression for the uncertainty of r. Okay, we've looked at a systematic method, a widely accepted method for computing the uncertainty in a measurement. And it depends on the partial derivative of the computation with respect to each of our measurements. For some expressions, analytically computing those partial derivatives is complicated, and so there's another way to do that. That is to find values for the partial derivatives, and that's a numerical approach. So here's an example that will illustrate this process. If we wanted to compute the flow rate through a Venturi tube, we have this equation that depends on two cross-sectional areas, A1, A2, the pressure drop, delta P, and density rho. Now if we want to find the uncertainty of the flow rate, we would use this equation for our function here of A1, A2, delta P, and rho. And we want to look at the effect of the uncertainty in our measurement A2 on the uncertainty in our flow rate. Say we measure A2 to be 3 inches plus or minus 0.01 inches. This should be 3 inches squared. And that means that the uncertainty in A2 is 0.01 inches squared. And in order to use this equation, we now need the partial derivative of r with respect to xi. So how do we get that? We're going to approximate it numerically. Quickly, numerical differentiation is shown here. We want to find the derivative of y with respect to x. Here's our function f of x, a graph plotting y versus x. And we approximate this as the change in y with respect to the change in x. or delta y divided by delta x. We are at a value x sub I, and we want to know what the derivative is there. We could approximate that by finding the change in y and dividing it by the change in x. So if we have xi and then xi plus 1, then we get values yi and yi plus 1. And here's our approximation. And you can see that if we have a smaller delta x, then we get a better accuracy in our approximation for the slope. So you can see here this isn't a very good approximation of the slope, but if we decrease delta x, then we end up with a better approximation for the slope. We could also go the other direction, where we vary x in the negative direction, and we end up with this expression for the slope approximation. That's examples of the forward difference and backward difference equations. So just rewriting the forward difference where we have delta x instead of this difference. So we'll show the slope approximation of the forward difference in terms of delta x. And now we have this expression for the approximation of the slope. So dy dx is approximately equal to y at x plus delta x minus y divided by delta x. So it's the change in y divided by the change in x. Now substituting r for y and xi for x, we get this. So here's our numerical approximation for the partial of r with respect to xi. Back to our example for flow rate. Here's our function, and we wanted to find the partial derivative of that function with respect to a2. Now we have all these measurement values for a1, a2, delta p, and rho. And we need to use these values because you see the function is going to have a different slope at different points. So we need to find the slope of q at this point in our space. Here we have r at our point. So we plug in our values for a1, a2, delta p, and rho. We get this value. And then r at our point plus some perturbation in a2. So we have a2 plus delta a2. So we plug in a2 plus delta a2 for a2 in this equation. And we're going to say delta a2 is 1 times 10 to the negative 4 inches squared. The smaller value we have for delta a2, the better our approximation is going to be. So we're not using the uncertainty here, we're using just a small value for delta a2. And plugging those in, we get this value. The units cancel out, leaving us with feet per second, 168 feet per second. But this is a partial derivative of flow rate with respect to area, so we'll just kind of change those units to 168 cubic feet per second per feet squared. So that's the sensitivity of Q with respect to area 2 at this operating point, 168 cubic feet per second per feet squared. Let's compare this with the analytical value that we would get. Here's our expression again, just rewriting that so that we could take a partial derivative with respect to a2. We come up with this. And now we can plug in our values for all the measurements to get an analytical result, and that gives us 170 cubic feet per second per square foot. So you can see there's some error, but with computers it's easy to compute the partial derivatives numerically, so this error is usually accepted in order to facilitate the uncertainty computation. Now in this video we've looked at the need for some systematic method of generating an uncertainty, and we found two expressions whenever we have a common form for our computed value, so for a product function or an additive function. And then since all these estimates depend on the partial derivatives, we looked at a numerical method for estimating the partial derivative whenever we want to do that.